All right, so homework 11 is a continuation of derivation and predicate logic, but we've added the quantifier equivalence rules to this, which allows us to break into negated quantifiers and get things done a lot more quickly. So quantifier equivalences, just like all the equivalences, are sort of the power tools of logic. And one of the things that makes them powerful is that you're allowed to substitute them within formulas, but you have to make sure that you're substituting them within actual woofs, that is to say subformulas that are actual woofs. So to give you an example of what you can do, if you have, for example, it's not the case that for all x, fx, then GA, you can, in one move, write there exists an x, not fx, then GA by the quantifier equivalence rule QE. So if this were line 1, it would be 1 QE. And the reason you can do that is that this is being substituted into by the other, and they are both legitimate formulas. That is to say, woofs. However, if you have a formula like there exists an x such that it's not the case that for all y not f x y, you're actually not permitted to write there exists an x such that there exists a y f x y by QE. And the reason you can't do that, the reason the rules don't permit you to do that, is because basically what you would be doing is substituting this formula for this, and this both are not woofs. It's not the case that for all y not fxy is not a woof on its own, because x is unbound. So you might think, why can't I do this? Because clearly these are equivalent, and clearly I couldn't be doing any actual harm. And the answer is just that equivalences require formulas to be equivalents, and there's no definition of equivalent non-woofs to work with. All right, so with that proviso, and on the assumption that you've acquainted yourself with the quantifier equivalences, let's go ahead and work on these. So it's not the case that there exists an x fx. If it's not the case that fc, then for all y not gy, show that for all x and for all y, it's not the case that fy or gz. Okay, so just like we experienced last time when we add equivalences to the propositional logic system, there's just a lot of ways that you can go about this. So you could start with the negation introduction if you wanted to, right? You could start with it's not the case that for all y, for all z, not fy or gz. As a hypothesis for negation introduction, that will totally work. And if you did that, you'd begin by applying quantifier equivalence to the hypothesis. But I'm going to do it a different way, which is really just following the basic advice that if you don't have to use negation introduction, don't. And you might remember that the reason for that is that it often results in a longer proof. So if I apply quantifier equivalence to line 1, I'm going to get for all x, it's not the case that f of x, right? 1 QE, and that will give me the antecedent of the conditional, not FC, so 3 universal elimination, which gives me for all y not gy by 2 for conditional elimination. Okay, so I've got not FC, and I could also get not GC, but if I went to GC, I would have a problem. Let's make it clear what this problem is, right? If I go to not GC by 5 and universal elimination, right, and then I'm anticipating the ability to use De Morgan's here, so I'm going to go not FC and not GC, so that's just 4, 6, and elimination, and then by De Morgan's I can have it's not the case that FC or GC, which is excellent, right? That's just 7 in De Morgan's. Now what do I want to do? Well, now what I want to do is add a universal. I want to do it 2 times in a row, right? So the first one is going to go what? For all Z not F, C, or GZ. And that's where we run into the problem, right? Can you articulate it? Okay, so the answer is that you can't just pick, when you're doing universal introduction, you can't just pick one instance of the name letter. To introduce on, you have to do it on every occurrence. So that doesn't work. It's easy to fix. You just go back and make sure to go to A instead. Okay, and so now we've got a legitimate use of universal introduction on 8, and we finish it with an also legitimate universal introduction on 9. So 9 and universal introduction. Okay, so did that proof seem right to you? If it did, then I snuck something by you. So can you go back and look and see what I did wrong? Okay, so technically it happened right here on line 9. I introduced the universal on C, but C actually is in an assumption. So I'm not allowed to do that. So what did I have to do to avoid that? Well, I just had to go back to 3 and reinstantiate to a different name. Could have been A, could have been B, but it can't be C. So we roll it back to here. We got 7, and we'll go to for all. We'll go to not F, B by 3 in universal elimination. And then the rest of the steps will work out just fine. Like that. All right, so number 2, it's not the case that there exists an f of x. It's not the case that there exists a g of x. Therefore, it's not the case that there exists an x of x. There exists an x such that f of x or g of x. This looks suspiciously De Morgan-y. Now, like before, you could definitely approach this through negation introduction, but I think you don't have to, so I won't. So on line 3, I'm just going to apply QE to get for all x not f of x. And that's 1 in QE. And then on line 4, I'm going to do the same thing to 2 and get for all x. It's not the case that g of x. So 3 and, 2 and QE. Okay, so I've got 2 universally quantified propositions, and that gives me the freedom to go to the same name if I want to in both cases, and I think I do want to, because I think what I want is not f of a, and I think what I also want is not g of a, 3 universal elimination, 4 universal elimination. So similar to the previous problem, not fa and not g of a, 5, 6, and introduction. Shake in a little De Morgan's. You got not f of a, or it's not the case that f of a or g of a. 7 and De Morgan's. No hypotheses to worry about, no names in either of the assumptions, so that permits me to go to, for all x, it's not the case that f of x or g of x, by 8, and universal introduction, right? And we're one step from home. It's not the case that there exists an x such that f of x or g of x. And that is 9 in Q, E. All right, number 3, for all x, it's not the case that there exists a y such that it's not the case that if fxy, then fyx. And we're supposed to show that it's not the case that for all x, not fa. Now here's an example of what I said in the very beginning of this review. It's very tempting to think that you could perform quantifier equivalence right here, right? But you can't, because this part that I've underlined is where what you'd be substituting for, and that's not a woof. All right, so once again, it's very tempting to start with the negation introduction here, and it definitely will work. Negation introduction always works if it's a valid argument, meaning if it is derivable at all. And it's especially tempting here because if you remove the negation from the conclusion, you get a universal, and the universal contains a lot of information, which might make you think that you could get the contradiction very quickly. So that's perfectly legitimate way to proceed. Once again, I will not proceed this way just to show that you don't have to. Part of the power of having these equivalences is that it allows you to avoid unnecessary hypotheses and to do things more quickly, therefore. So on line 3, I'm going to go ahead and say F. I'm not going to go to A because it's already in an assumption. So I'm going to go FAB, hypothesis for existential elimination. And now I have to think a little bit about what I want to do with regard to the universal, because I could go to B or I could go to A. But if in my mind I convert this negated existential negated, and I stress in my mind because I can't do it according to the rules, I see that I've got 2 universals for all x and for all y. And so by going to B and x, I'm going to replicate the antecedent of this formula. So let's go ahead and say it's not the case that there exists a y such that it's not the case that f by then f y b. Let me just stop and make another observation about the rules. It's also true that it would be tempting here to apply negation, something like negation conditional, right, to this part of the formula. But once again, you can't. And the reason you can't is the same reason we've been discussing, is that this is not a woof. So since it's not a woof, it's not a subwoof. Okay, so that was by 1 in universal elimination. And now I can apply QE. So for all, if FBY, then FYB, and that's by 4 in QE. And that allows us to go to FBA, then FAB by 5 in universal elimination, giving us FAB by 3, 6 in conditional elimination. Okay, so I've got FAB. What I want is it's not the case that for all x, not FAX. Very simply achieved. There exists an x, FAX, 7, existential introduction, remembering that with the existential there are no restrictions. And then by QE, we have it's not the case that for all x, not FAX. Our conclusion. 8 in QE, and are we finished? No, we are not, because we're still in a hypothesis, but we are awfully darn close. It's not the case that for all x, not FAX. Repeating, and that's 2 and 3 through 9. Existential elimination. Okay, number 4 is an argument from no assumptions, in other words, a theorem. And if you look at it, you'll see that the main operator is a conditional. And the best way to proceed with these typically is to hypothesize the antecedent of the conditional. So it's not the case that for all x, there exists a y, fxy, hypothesis for conditional introduction. And we have to derive now the consequent. The main operator is a conjunction, which tells us that we'll probably be deducing each conjunct separately, probably from some instantiation of the hypothesis. Okay, so this is a negated universal, which goes to there exists an x, such that it's not the case that there exists a y, fxy by 1 in QE. And now we have an existentially quantified formula, which we need to hypothesize to some name. Now, you'll notice that the conclusion contains A and B, and that actually does not put any restrictions on us at all. But there are times when it could, especially if, for example, we were introducing a universal. Now, it looks like here we're going to be introducing an existential, but maybe let's just go ahead and go to C. And if C doesn't work for some reason, we'll go back and think about Y and whether or not we should use A or B. So it's not the case that there exists a Y such that F, C, Y, hypothesis for existential elimination. Now, this might seem like a strange time for me to remind you of this because we're pretty deep now into derivation and predicate logic, but I've noticed in the past that sometimes people just forget that there is no such thing as existential elimination that works analogously to universal elimination. So it's really, really important to remember that. You could just forget because it seems like if you did it, the proof would be so easy. But just remember, there is no case when you can just go, for example, from there exists an x, f of x on line 1 to f of a on line 2 by existential elimination 1. There is nothing like that. That's bad. Don't do it. Remember. Okay, so now we have a negated existential, and that, of course, so that's going to go to for all y. It's not the case that fcy, and that'll be by 3 in QE. And now it's time to start thinking about creating these two conjuncts, right? And we'll go back to the well twice here. So we'll get, it's not the case that FCA, and we'll also, it's not the case that FCB, both by 4 and universal elimination. And then we'll just slap existentials on them. So there exists an x such that not FCA and not FXA, and that is by 5 and universal existential introduction. And then we will have, there exists an x such that not fxb, and that is by 6 and existential introduction. Just put these together and you've got your proof. Right, and you're done except for two things, namely discharging both of these hypotheses, right? So how do you discharge the existential? You just have to take away the indent and repeat. So 2 and 3 through 10, existential elimination. And then you just have to get rid of the original hypothesis by conditional introduction. So drop the line and 1 through 10, conditional introduction. All right, number 5, proof of another conditional. So strongly suggesting the previous approach. So there exists an x, g, x, x hypothesis for conditional introduction. Now, if you stare at this one for a second, you'll notice something weird, which is that we're now supposed to derive, it's not the case that for all x, f of x, but there is no f in the premise, and there is no f in the hypothesis. So if this is possible, it's really only going to be because the lines 1 and 2 are contradictory, and that means that we'll use the con rule. So in this case, you could have gone for a negation introduction proof, but it's a little weird when you're in the middle of a negation introduction proof and you see a contradiction that you didn't even need the negation introduction hypothesis to generate. No harm, it just can kind of weird you out. So this is going to go quite straightforwardly. Go ahead, there's no names here, so go ahead and go to GAA, right, by 2 and existential elimination, right? Wrong, I just said, okay, there's no such thing as that. So hypothesis for existential elimination. Okay, and then we've got for all x, it's not the case that there exists a y such that g xy by 5 and QE. Well, how about not 5? How about 1? Okay, and on line 5, we'll instantiate the universal. So it's not the case that there exists a y such that G will go to A, since there's no names in this. It's not the case that there exists a y, G, A, Y. So that's 4, and universal elimination. Same process for all y, not G, A, Y. 5, QE. And then on line 7, you can go to any name you want, but clearly if you go to A, you're going to get a contradiction, so not GAA, right? 6, negation, universal elimination. And so you got your conclusion, so you can just pull the conclusion. It's not the case that for all x, fx out of your nose by 3, 7, con. Okay, so punch out of your existential elimination with that formula. Two, 3 through 8, existential elimination, and then the whole thing, 2 through 9, conditional introduction. All right, number 6 is actually really simple to do in 6 steps directly, just using quantifier elimination and De Morgan's and material implication. But let's try to do it in a way that's maybe a little bit more entertaining. So when we're proving universally quantified conditionals like this one thing you can do is approach it using conditional introduction and then doing a universal introduction at the very end. So if you approach this problem in this way, you would go to f of A, hypothesis for conditional introduction. And then your task would be to deduce not G of A. So suppose we did this by hypothesizing G of A, hypothesis for negation introduction, and this would give us FA and GA, 2, 3, and conjunction introduction, which would give us, can you see how this is going now? There exists an X such that f of X and G of X by 4 and existential introduction, which gives us a contradiction with 1, and this is a nice time to use the contradiction rule rather than have to write out this long contradiction. So P and not P by 1, 5 con. So that gives us our not GA, drop a line, 3 through 6, negation introduction, which gives us if FA, then not GA. 2 through 7 conditional introduction. So the last step is simply universal introduction. On line 8. And what's good to see about this proof is the reason you can do universal introduction here, and that's because A, although it was introduced in a hypothesis, is ultimately reoccurring in line 8 after the hypothesis has been discharged. So it's no longer an undischarged or live hypothesis, and that's why it's okay to do universal introduction on 9. So that's one of the basic proof techniques. It's not something you had to do here. In fact, it made the proof longer. It's a good time to introduce it. All right, number 7 also has a very straightforward solution, simply through quantifier exchange on the assumption and then existential elimination. But let's, and I'll post that actual solution. So if you want the simplest solution, just go to the static document. Now let's see again if we can take a more interesting and instructive approach to this one though. So suppose we decided to approach it through negation introduction, which we would do by hypothesizing for all z, g, z, hypothesis for negation introduction. And then the obvious thing to do is do GA by 2 in universal elimination. So do you see a root from here? Why don't you play with it a little bit and see if you can work it out. So suppose from here you went with or introduction to it's not the case that there exists a y f y or g a. 3 or introduction. Now that might feel a little unintuitive, but it's obviously legit. And of course then with material implication you can change that to there exists a y f y then GA, right? So that's 4 and MI, and then universal introduction will give you for all x there exists a y f y then gx, so that's 5 and universal introduction. And what do we have? We have a contradiction between line 1 and line 6, so just go ahead and write P and not P. 1, 6, con. And that gives us, it's not the case that for all z, gz. Two through 7 negation introduction. So usually negation introduction proofs are longer than the alternative when the alternative exists, but actually this one is exactly the same number of lines as the more straightforward approach that I'll put in the solutions. All right, another theorem. There exists an x f of x, or there exists an x such that not f of x. You would think that would be a necessary truth in the semantics, and therefore a theorem here. But make sure you realize that this actually doesn't have the logical form P or not P, which we call the law of the excluded middle, which is a tautology and easily derived. To have that, you would have had to have the negation on the outside, right? But still, it feels very plausible that there is something that either has f or something that does not have f. So the straightforward approach to this one is going to be with negation introduction, right? Negate the entire formula like this. It's not the case that there exists an x fx or there exists an x not fx, and try to derive a contradiction. That is the approach that I will put in the solution document, but let's approach this one in a different way here. So in the past I've spoken of using conditional introduction when what you're trying to prove is a disjunction, and just introducing or using material implication at the end. So if you were to do that here, you would say, one, hypothesis, it's not the case there exists an x fx, and that would be a hypothesis, but not for negation introduction, but for conditional introduction. And then what we're going to try to do is derive there exists an x not f of x. So what does this look like? Well, it's not the case that there exists an x f of x, so for all x not f of x by 1 and quantifier exchange, and that gives us not f of a by 2 and universal elimination. You see how this is going to go? So that gives us there exists an x such that not f of x by 3 and universal introduction. And was this okay? Yes, because a is not in the hypothesis. So we've just shown that if it's not the case that there exists an x f of x, then there exists an x such that not f of x. 1 through 4, conditional introduction. Now, using material implication here is actually not just a one-step process, but a two-step process, right? Because it tells us, material implication tells us that if P, then Q is logically equivalent to if not P or Q, right? So to use the rule here, we have to make this not there exists an x f of x, or there exists an x not f of x, right? And that's what we get through material implication, right? Not exists an x f of x is your P here, right? So not P is not there exists an x f of x. And then you have to finish it off with double negation. So there exists an x f of x, or there exists an x not f of x, 6, double negation. And this is a perfectly legitimate use of double negation, right? Because you're applying it to this sub-formula, and this is a true sub-formula. It's a true woof. And so you can make this substitution using the equivalent. So this is a cute little proof technique, and actually this proof is a few lines shorter than the more straightforward derivation that I give you in the notes, the solutions rather. All right, number 9 is just an opportunity to use a bunch of our equivalences. We'll just approach this straightforwardly. So you're being asked to derive there exists an x such that not hx, and hopefully right now you're thinking, okay, that probably means we'll get not ha or not hb and just do an existential introduction. So if you apply quantifier exchange to number 2, you're going to get there exists an x such that not kx and gx. So 2qe, and that means you're going to hypothesize to it's not the case that ka and ga, a is not in a hypothesis or an assumption. So hypothesis for existential elimination. Now we're looking for not HA, that's certainly not in line 4. So why don't we go ahead and universally eliminate to FA for HA, then GA and KA. So that's by 1 and universal elimination. And if you're having a thought, why didn't we do universal elimination before we did the existential elimination hypothesis? That's a perfectly good thought. We could have done that. And in the event that we needed to use this formula on line 5 outside the context of this hypothetical derivation, that would have been an intelligent thing to do. It just so happens that we don't need to here. And even if we did, we could always just reinstantiate. So now maybe you see an interesting possibility here through the use of modus tollens, but you can't do it yet because it's not the case there. Ka and Ga is not the same as Ga and Ka. They are logically equivalent, but you have to apply the COM rule explicitly. So line 6 is going to be, it's not the case that GA and KA, I called it the COM rule, but it's the COM equivalence, commutation. So 4 COM. And now we can get, it's not the case that FA or HA by 5 and 6 and modus tollens. And now you can see we're getting pretty close to our goal. Shaken little De Morgans, not FA and not HA, 7 De Morgans. And then out pops not HA. That's 8 conjunction elimination. Now, just to remind you, we can't punch out with not HA, right? Because A is in the live hypothesis. So we do have to, right, do there exists an X, not HX here. So 9 existential introduction, and then punch out on line 11. There exists an X, not HX. 4 through 10. Excuse me, that's 3, 4 through 10. Existential elimination. Okay. All right, and number 10, the last one in this set. Given two assumptions. One tells us that it's not the case that there exists an X such that X fx. If you wanted to make this meaningful, you could say it's not the case that there exists an X such that X is funnier than X. So nothing is funnier than itself. And the other assumption is that for all x, y, and z, if x is funnier than y and y is funnier than z, then x is funnier than z. So we call it transitive relation, right? If A is funnier than B and B is funnier than C, then A must be funnier than C. Transitivity is an important property. It certainly doesn't hold of all relations. For example, it doesn't hold of loves. If A loves B and B loves C, it certainly doesn't follow that A loves C. But what we're being asked to derive is that it's not the case that there exists an X and there exists a Y such that X is funnier than Y and Y is funnier than X. Now remember, strictly speaking, when you're doing derivation, you're just doing symbol manipulation. So assigning actual interpretations to the predicates here is, strictly speaking, illicit. All right, so really I think the only way to approach this one is through negation introduction. So we're just going to go ahead and hypothesize that there exists an X and there exists a Y such that fx y and fyx. Hypothesis for negation introduction. And then we have a formula with two existentials, so to get any value out of it, looks like we're going to have to do two existential hypotheses. So the first one, there exists a y such that fay and fya, noting that A does not occur in any previous assumption or hypothesis. So that's the hypothesis for existential elimination, right? And then we just do it again. So then, although we can hypothesize anything we want, any time we want, if we're doing this for existential elimination, we should definitely make sure and go to a different name. So FBA, FAB, and FBA. So that's hypothesis for existential elimination. So we're three hypotheses deep. And then basically you just need to stare at the second assumption and see if you can instantiate it in a way that's constructive. And this doesn't take a lot of staring. You can see that if you instantiated it to FAB and FAB, then FAB and FBA, which is line 5, then out would pop FAA. And you could just do an existential introduction on that, and there would be your contradiction. So let's go ahead and just do that. So that's 3 steps. Later on, when we're doing more advanced stuff and we're all very comfortable with these rules, we'll start combining some steps, but for now we are not. So first step, for all y for all z, if fay and fya, then faz. Second step, for all z, if fab and fba, then faz. And then FAB and FBA, then FAA. So 3 universal eliminations in a row. So that gives us FAA, right? As we said, 5, 8, conditional elimination. And now you can achieve the desired contradiction in one of 2 ways. You can throw on an existential here, or you could do a quantifier exchange on line 1, right? And then a universal elimination to get not FAA. Now, in the solution, that's the way I do it. But here, I'll just do it differently. Go ahead and do there exists an X, F, X, X, 9, existential, introduction. And we have our contradiction. You could write the contradiction as conjunction introduction on 1 and 10, but the lazy and convenient way is just P and not P by 1, 10, con. Right? Now, actually, if I had worked toward FAA and not FAA, it wouldn't have been merely lazy or space saving to write P and not P. I would really need to use P and not P because I would need to get AA, or I would need to get A out of the final line in order to be in compliance with the restrictions on existential elimination. Okay, so we got a contradiction, and we actually want to punch out with this contradiction, not just once, but twice. So I'm going to write P and not P. And that's 4 and 5 through 11, existential elimination. And then I'm going to write it again, P and not P, and that's going to be 3 and 4 through 12, existential elimination. And so now I've got my P and not P for my negation introduction, and so I can finish this up by negating the hypothesis. It's not the case that there exists an X and there exists a Y, such that Fxy and Fyx, right? And so the final line, discharging our negation introduction hypothesis, and that's 3 through 13, negation introduction. And there we go.